two substances together, when you put two substances together that do not react together, then we say we have mixture. We have two types of mixture. We have homogeneous and heterogeneous mixtures. Homogeneous mixtures are solutions. Heterogeneous mixtures are homogeneous mixtures are a kind of mixtures. Solutions are a kind of mixtures. And I gave you some examples of mixtures. Tea in a cup is a mixture right in water, but tea in a cup is more of a solution than is a solution. Yes, solutions are a kind of mixtures, but a special kind of mixtures. Sand in water is an heterogeneous mixture. It's not. So for mixed solution, you say they blend well. And that's the main difference between solution and mixture. And then I went on to talk about solubility. So I went on to talk about solubility. Solubility has to do with the amount of a specific substance that can dissolve in a specific amount of solvent under certain conditions. And I looked at we tried to interpret solubility curve, and we also looked at factors affecting solubility. And we said three major factors affect solubility. We have the solute-solvent interaction, temperature effect, and pressure effect. And I said solute-solvent interaction, under it, we have two sub things that affect two sub things that affect solute-solvent interaction. Number one is the molecular mass or molecular weight, and the other one is the polarity. Molecular mass is very significant when you're talking of gases. So as the bigger the molecular mass of the gas, the molecule, the higher the solubility. Why? We've talked about surface area, that the bigger this molecular weight, the surface area will be larger, and so interaction is more intense, and so solubility is higher. That's the reason for why bigger molecular weight of gases with bigger molecular weight tend to dissolve more because they have larger surface area. This can be a question. Why is it that krypton will be more soluble than oxygen? Krypton has it's one of the lower elements in its group. So it's why oxygen is higher. So you know that molecular weight increases down the group. So the molecular weight of krypton is higher. And so since it's higher, it will have more surface area. So it can react with the solvent, thus dissolving faster. So its solubility would be higher. Now, when you're dealing with liquid, polarity is very significant. Liquids in solutions, solutions that are liquid in nature, polarity is very important because when there's polarity, so when you have oxygen, nitrogen, and fluorine, they're the most electronegative elements. They will pull the bonds to themselves, thus making a slight charge in the molecule. And when there's that kind of charge in the molecule, then there will be polarity. And then, so because it's now partially polar, it will also be attracted to polar solvent. So polarity plays a role. And when you're talking about polarity, there are certain things you should think about. If you are dissolving a polar solvent, if you're dissolving a polar solid in a polar solvent, yes, because of the polar dipole moment that causes the charge in the molecule, it will now make it polar, and so it will dissolve in a polar solvent. I also define the concept of solute and solvent. When in a mixture, the substance that is more is the solvent, and the substance that is less is the solute. And so we said polar solutes will dissolve completely in polar solvent. In non-polar substance will dissolve better in non-polar solvent. And certain things to consider, we're giving some examples. When you see CC bonds, you can know that there's non-polar. But when you see CH, there's tiny polarity because the electronegativity of carbon and hydrogen is close, but not exactly the same. So these are things you used to begin to predict whether something is polar or not. But when you see lots of highly electronegative compounds attached to carbon, you know that substance is most likely going to be polar. So hexane is just nearly polar, but more non-polar. It's more of non-polar. Yes, there are CH bonds, but the polarity is insignificant. So in hydrogen, there are lots of CH bonds, so it will be non-polar and to be insoluble in water. That was where we stopped. So we want to look at the effect of temperature. So I've finished talking about solvent solute interaction under molecular weight and polarity. Now I'm going to number 2 that affects solubility, temperature. So for solids, the solubility of solid in liquid is greatly affected by temperature. As the temperature increases, the the will increase. As the temperature decreases, the solubility will decrease. Now look at that supersaturated substance we talked about in our last class. I introduced the concept of saturated, unsaturated, and supersaturated. Now think about a saturated substance that you know that you've reached the saturated point. That's such that if you add one more drop, there will be crystals under because it's saturated. Saturated substance is the point whereby the solvent has taken the maximum amount of solute it can dissolve, above which you begin to find crystals. That is saturation. So when you've got to a point of saturation and you decrease the temperature, you maybe freeze or cool, put ice block, you see crystals because you reduce the temperature. So the solubility has decreased. So you now have a supersaturated solution. If you further decrease that temperature, you see more crystals. If you eat that substance that had crystals under it, that was supersaturated, if you heat, don't be surprised. All the crystals, or most of the crystals will dissolve because the solubility has increased. So when you increase temperature, solubility increases, especially for solid dissolving in solvents, in liquids. But for gases, you see, so for liquids, for solid, so temperature is very significant. Temperature increases their solubility, but it's opposite for gases. For gases, when you increase the temperature, solubility will decrease. And that's why you keep if you hit a balloon, just imagine hitting a balloon, it will burst. If you put you've disabled me, I can't share screen. Who is now the host? Oh yeah, please put me back as the host. When I was logged out, the internet threw me out, and one of you is now the host. Please make me back the host. Okay. Thank you very much. So sorry about that, internet issues. So again, I was saying that yes, for solids and liquid, when you increase the temperature, solubility will increase. But that's not the case. That's in contrast with gases. When you increase the temperature, the solubility decreases, because when you increase the temperature, the gas the gas expands. The gas expands and becomes more volatile. So solubility will increase. So it's opposite. For solid and liquid, increase in temperature increases solubility. But for gases, increase in temperature decreases the solubility, because increase in temperature causes the gas to expand and become more volatile. So when it's more gaseous, more volatile, solubility will decrease. Look at this casing example. This is a real life data got from the lab. See, KCl, as you increase the temperature, before only 27.6 grams dissolve at 0 degrees Celsius. As you increase the temperature, 34 grams dissolve in 100 grams of water. As you increase the temperature, 42. As you increase the temperature, 57. If you keep increasing the temperature, you'll be able to dissolve more. And so if you decrease the temperature, more will crystallize out of the water. Same thing for sodium nitrate. But for gases, that the opposite is it. As you increase the temperature, less of it is able to dissolve. See the trend. You see, as you increase the temperature, the amount that dissolves in it is reduced. So for gases, solubility decreases with increase in temperature. That's why when you shake your bottle of Coke, you are increasing the temperature. When you shake it, you're increasing the temperature, you're agitating it. And so when you open it, pop, you see your gas coming out, because your Coke is a solution of gas and liquid. So you've increased the temperature, and so it will come out. Why would a bottle of carbonated drink like Coke, Fanta explode when left in a hot sun? It's obvious. Like I said, in the hot sun, solubility has decreased. So all the gases in the Coke have come out, and they will expand. They will collide with each other, expanding. And so if there's no space, it must come out. So it will break especially with glass, wow, it will break it and come out. Why is a moving tire more prone to busting than a stationary tire? Already explained when teaching. Because a moving tire, if the tire, especially if the tire is bad, weak, or expired, generally in all tires, as you move, especially on sunny day, the gas in the tire expands. It expands, it collides itself, it keeps expanding, it's looking for a way out. So it's exerting more pressure on the walls of the tire. Now, if the tire is bad or not very good, and you are moving fast, you are hitting it up faster, then the pressure is enough to burst the tire. So that's what's happening. Why would fish die in a water that gets too warm? Somebody explain to me why. Hello, let's be an interactive class. Somebody tell me, why do you think a fish would die in water when the water gets too warm?
Because the solubility of oxygen gas is going to reduce, and the oxygen gas will come out of the water. The fish will not have enough oxygen to breathe, and it's going to die.
Correct. If you are near me, I'd have given you a high five. Thank you so much. Very intelligent answer. So that is it. So the fish, before it will even die of the heat on the body, would have died of suffocation. Because when you heat the water slightly, they have not even heated it enough to cook the fish, but just a little heat, the oxygen level in the water will reduce. The oxygen level in the water will reduce. When the oxygen level in the water reduces, the fish, because the oxygen will reduce because there's expansion, it becomes more volatile, and so it becomes less soluble in the water. And so the fish has no dissolved oxygen to breathe. It will die. And then when it dies, and you continue heating it, you start cooking the fish. So that is what is happening. And that's why we are saying global warming is a problem. Global warming is going to reduce biodiversity, because many animals will not be able to. Global warming, the temperature is gradually getting hotter than it's supposed to be. And so with time, there will be loss of biodiversity. The animals that can stay in certain regions will no longer be able to stay there, because they no longer have, especially in the water bodies, will no longer have oxygen to breathe, they will die. So only few fishes that can stay with less oxygen will survive. So in a river where they have 10 different types of fishes, maybe you only have the three that can survive hard conditions. And so with time, there'll be lots of food, because that fish before, he has another smaller fish he eats, that eats the smaller fish that eats the tiny worms, that eats the grasses and fungi in the water. Now, only the big fish that can survive is there. That fish, the hunger will catch it because it will not be able to eat the food it normally eats. So it might even die of starvation. So global warming is a very big issue. And so they are all intertwined. So this is, we're looking at it now. This is, I told you, solubility graph are plots that shows you the solubility in relationship with temperature. So you see, as the temperature is increasing now, the solubility of the gas is reducing. See now, unlike when we looked at solid, let me go back to that. When we look at solubility curve for solid, you see it was increasing as temperature increased. See, did you see that? It was increasing as temperature increased. But gases, you see that the shape is different. So in the exam now, I can give you two solubility curves. I won't put the name. I'll say predict which of these do you think is for a gas, and which of this solubility curve do you think is for a solid or a liquid solution. So if you've listened to my lecture and understood well, you, based on the shape, you say, oh, this must be for a gas and that must be for a liquid or solid solution. The last of the effect, that things that affect solubility. You know, I said solvent-solute interaction, temperature effect, and pressure effect. These three things affect the solubility of substances. Under solvent-solute interaction, we talked about polarity and what? Polarity and I have a polarity and molecular weight. Molecular weight. Under solvent-solute interaction, we have polarity and molecular weight. So in all, they are just four. They are just three. But under solvent-solute interaction, you have sub things that affect it, which is the polarity and the molecular weight. And so under pressure, pressure again affects solubility, especially for liquids. It has no effect on gases, but it has a lot of effect on liquid. Pressure affects the solubility of liquid. There's nothing to press in a liquid. If you press it, it will leak. If you press a solid, it will break. But for gases, if you press it, you are forcing the gas to enter into the other phase, and so solubility increases. So pressure affects the solubility of a gas. And the law that relates the pressure to solubility of a gas is what we call Henry's law. Everybody say Henry's law. I want to hear some people talking. Henry's law. Nobody's talking. Henry's law. Henry's law is the law that relates. Henry's law is the law that relates the solubility of a gas to the pressure. So for pressure has no effect on the solubility of solids. It has no effect on the solubility of liquid, but it has a very significant effect on the solubility of gas. Please mute yourself. On the solubility of gas. Please mute yourself. So when pressure increases, solubility of liquids and solid, no change, but increases the solubility of gases. When pressure decreases, no change on solids or liquids, but it decreases the solubility of a gas. When temperature increases, it has effect on both solid, liquids, and gases. When temperature increases, it increases the solubility of solids and liquids, but it decreases the solubility of gases. When temperature decreases, it decreases the solubility of solids and liquids, but increases the solubility of gases. This is a summary of all I've been trying to say since we started this lecture. Let's take, why does increasing the temperature of a solvent speed up the dissolution process? Yes. Why does? The reason for that is because as temperature increases, solubility increases. So when you increase temperature, the dissolving of a solid or liquid solid will increase. How does solubility of a solid change when temperature of the liquid is increased? How does the solubility of the solid change when it increases? It increases. A salad or trail mix is an example of what kind of mixture?
Homogeneous.
Salad.
Heterogeneous. Heterogeneous
Salad
mixture.
mix.
Heterogeneous, not homogeneous.
Heterogeneous.
Heterogeneous, excellent. What kind of solution are made when a solution temperature? What kind of solution are made when a solution's temperature is increased? So do you think if you had a saturated solution and you increase the temperature, what kind of solution will it give rise to? If you had a
Unsaturated
saturated
solution.
liquid solution and you increase the temperature, what type of solution do you think you will make?
Unsaturated.
Unsaturated
Excellent.
solution.
If you had a supersaturated solution and you increase the temperature really, really high, what kind of solution do you think it will bring? Probably a saturated or unsaturated solution. Yes.
Can become saturated or unsaturated.
Unsaturated, yes. Yes. Look at this calculation. Let's calculate it. Oxygen, all of you, your biros and try and calculate it. Oxygen is less soluble in water than carbon dioxide. Do you agree with me? Why?
It's not showing your phone.
We looked at this case. Just we have not started solving it. Oxygen is less soluble in water than carbon dioxide. Why do you think so?
Are you saying YouTube? Anyway.
Because it has
I think they're only 58.
Now let's look at it. The molecular weight of oxygen molecule O2 is 32. Carbon is 12. And oxygen is 16 times 2. Oxygen is 16 in carbon dioxide. So you have 16 times 2. So that's what? 12 plus 16 plus 16. That's what? 32 plus 12. 32 plus 12, 4. 44. Carbon dioxide is 44. Oxygen is 32. So based on our discussion, which one do you think will be more soluble?
CO2.
CO2 should be more soluble than oxygen. Why do you think it's more soluble? From our knowledge. Yes, it has a bigger molecular weight, so its surface area is larger, so that makes it more soluble than oxygen. So they are just stating a fact that you already know. Oxygen is much less soluble in water than carbon dioxide, and we now know the reason why. And the solubility of oxygen is given as 0.00412 gram per 100 ml at 20 degrees Celsius at 760 milligram per hydrogen. Calculate, so they gave us the solubility of carbon dioxide. Calculate the solubility of oxygen gas in 100 ml of water at 20 degrees Celsius and at a pressure of 115 millimeters mercury. Now the Henry's law that relates solubility and pressure is given as this. C is equal to Kp. K is your constant, P is your pressure, C is your solubility, that's your concentration. Solubility and concentration are about the same thing. Concentration, we usually say mole per dm cube, but in concentration, solubility, we usually say mole per liter, and you know that liter is the same thing as dm cube, so they're about the same thing. So you have C is equal to Kp. K is a constant, the Henry's law constant. So we have our solubility here. So we'll first get K and use the K to calculate solubility of oxygen. Since the temperature is the same, we wouldn't have been able to use the same K if the temperature was different, but the temperature is the same, so we can use the same K. So we have that C is equal to Kp. C is equal to Kp, and our C is 0.00412 is equal to K. We don't know the K, and we know that the pressure is 760 mm Hg. So can we not find K? Hello? Are people with me? Can we not find K?
Yes, ma'am, we can find K.
So when you find the K, you now put this same equation, C is equal to Kp. Now you have your K, you have your P. So what you don't have for the next part is your C. And so you can find the C, that's the solubility of oxygen. I hope I've explained how to solve that question.
Yes, ma'am.
Yes, ma'am.
So, number 6, lemonade, soda, and salt are some examples of what?
Homogeneous mixtures.
So what is homogeneous mixture? So in OBJ, I say homogeneous mixture, solution, heterogeneous mixture, all of the above. Which one is the most appropriate answer?
Solution.
Excellent. Excellent. So this is the answer. So that calculation, by the time you do it right, this is the answer you get. Zero. So take note of the answer so you solve it. And you might start from there in our next class. Take note of the answer, 0.00623 gram per 100 ml. If you have a problem answering the question, you can still ask me or the next lecturer if I'm not the one taking it. So I'm sharing another slide now.
This is what I know. The need to know for his class, but work for this one.
So you are now gurus into explaining solubility, solution concept on that saturation, saturation, and supersaturation concepts. You now know the law that relates solubility of a gas to pressure. What is that law? I can ask it in OBJ. The law that relates solubility of a gas to the pressure. One, Henry's law, gas law, Raoult's law, ideal gas law. What is the answer?
Henry's law.
Please mute yourself. Yes? Are you with me? I can ask in OBJ. The law that relates solubility of a gas to pressure is A, Raoult's law, Henry's law, ideal gas law, Boyle's law. What's the answer? Are you with me? I can ask the law that. What's the answer?
Sorry, we're getting echo.
Somebody is using you. Two people are near each other and they're listening to this lecture, or somebody is listening to you and listening to my lecture. That's what's happening. So the person is mute everything you're using. And if two people are together, one person to switch off his speaker. That's what's happening. Anyway, two people listening to the lectures on their various devices. All right, so we move to the continuation of the lecture. So want to look more at Henry's law. So Henry's law states that the solubility of a liquid, a gas, in a liquid is directly proportional to the partial pressure of that gas over the solution at constant temperature. The solubility of a gas in a liquid is directly proportional to the partial pressure of that gas over the solution at constant temperature. So let's look at Coke is our ideal solution here now. So they're saying the solubility of the gas inside the Coke is related to the pressure you put on top of the Coke. Is related. So like for example now, if or let's look at a piston. Assume we have a piston where they put Coca-Cola mixture and they put plenty gas. So they press the gas on top of the liquid. They press it. The more they press it, more gas will be dissolved inside the liquid. The more you press it, more gas will be dissolved. But if you lift the piston, more gas will come out of the liquid and just begin to play on top of that liquid. That's what we're trying to explain. So K is the Henry's law constant. P is the partial pressure. And we've solved one question using it already. So when the partial pressure drops, the solubility of the gas drops to maintain equilibrium. Again, look at that piston. When you are adding pressure, solubility is increasing. Now you reduce pressure, solubility, because some gases will come out. Some children are like that. If you don't punish them to read, disturb them to read, they will not read, they will fail. But if you give them a lot of pressure, read, a lot of incentive, they will pass well. If you relax, they too, they will relax. That's how these gases are behaving. Okay. So this can be used to calculate the molarity of a gas. Okay, so Henry's law, Henry's law is dependent on certain things. The temperature of the gas, the partial pressure of the gas over the liquid, the nature of the solvent, and the nature of the gas. So Henry's law is dependent on 4 things. What are the things though?
Temperature,
Partial pressure of the gas over the
liquid, the nature of the solvent, the nature of the gas.
Excellent. Thank you very much. I want you to say it again so that you will not forget. Yes, let's go. Yes. The 4 things that Henry's law is dependent on are what?
Temperature,
Temperature of the
temperature of the liquid, the partial pressure of the gas over the liquid, the nature of the solvent, the nature of the gas.
So the most common, you can mute yourself so that we can hear. The most common solvent is water, and we know that carbonated drinks, that's like Coke, Fanta, they are real life examples of Henry's law in our everyday life. In those drinks, carbon dioxide are dissolved inside it. A lot of carbon dioxide is cooked under pressure. So that's why when you shake it, you see that you shake it and you open it up, the CO2 wants to come out, and that's what leads to the pouring out of liquid. Now, even if you don't shake it now and you quietly open it, you are reducing the partial pressure. So when you open it, the gases come out. The purpose of those gases is to make the drinks fresh when we taste it. So when you open it, that's why when you open the Coke and you drink it, cold Coke, you feel refreshed. But if you open the Coke and leave it, after some time, you drink it, it doesn't taste fresh because the CO2 must have all gone out because you reduced the partial pressure. So solubility has reduced. So you drink it, you notice that something is different about this Coke. There's nothing different. What happened is that the CO2 has come out. And the purpose of the CO2 is to give us that satisfying feeling, that fresh feeling. That's what happens. That's why we all like cold drinks. Cold drinks. When you take a cold drink, what is happening is that more of the CO2 is dissolving the air. So when you take it, it feels satisfying. It feels so fresh. It's the effect of solubility. Henry's law at play. That's what's happening. And so we've explained all this. So to maintain equilibrium, if you reduce the pressure, solubility will decrease. If you increase the pressure, solubility increase. That's what that picture is all about. So this is an example of a solution we want to calculate. Nitrogen gas in water at 25 degrees Celsius and at this pressure is this. Calculate the solubility when the pressure is doubled. Very easy. You just double the pressure. So you just double the pressure. So you use this setting to calculate your K. This is like the other one we calculated. Use it to calculate your K. When you calculate your K, you now use the K to calculate the solubility. But here, yes, so that's what happened here. Use these 2 equations to get your K and use your K to calculate the solubility. Look at this example again. The solubility of, this is full. This is not the same question, but here this with solution. It's the same question, but here I've calculated it. So I've explained how to calculate it. We can't sleep here. Remember again, C is equal to Kp. So if you calculate your K, use your K to calculate the C. Everybody take a screenshot of this and try it out. We can't sleep here. Everybody take a screenshot of this work and practice it, this particular work. Practice it. Now, I need you to note that Henry's law only works if the molecules are at equilibrium. Henry's law does not work for gases at very high pressure. At very high pressure, the gases become liquids themselves. So Henry's law only works when the pressure is not so high. But when the pressure is so high, Henry's law may not work. Henry's law only works if molecules are equilibrium. So you increase the temperature, you increase the pressure, they balance. You reduce the pressure, they balance. You increase the pressure, they balance. You reduce the pressure, they balance. But if you increase the pressure so much that it cannot balance, it cannot be reversible, you are not obeying Henry's law. Henry's law does not work when there's a reaction. If there's a reaction, it won't work. For example, if you bring hydrogen gas and chlorine gas and you are making them to dissolve in each other, it's reaction that will take place, not that type of interactions. So for Henry's law is only applicable to solutions, not reactions. Once there's going to be a new compound formed, Henry's law will not obey. So Henry's law only works for solutions, not for when reactions take place. So these are exemptions to the Henry's law. Henry's law does not work when the equilibrium cannot be set. Henry's law does not work when the pressure is so high. Henry's law will not work when there is reaction, when the two entities are reacting. And in nature, we know that as concentration and partial pressure increases, we have deviations from Henry's law. They begin to be very noticeable. This is very similar for many gases, and gas law. As we begin to deviate from ideal laws, the predictions of gas laws do not hold for many gases. So for many gases, for many gas laws, there are usually points of deviation. That's what I'm trying to say. So the gas laws usually obeys, only ideal gas obey all the gas laws 100%. But real gases have points of deviation from all the gas laws. So Henry's law is not an exception. And deviation occurs, like for when you move from ideal gases, deviations begin to occur when the pressure is very high and temperature decreases, especially for ideal gas. So for this reason, solutions which are found to obey only dilute solutions obey gas laws. Only dilute solutions obey gas laws. Only dilute solutions obey gas laws. Did you get what I said? I said gas laws, just like every other law, has points where they begin to deviate, where gases begin to deviate from their law. And so our Henry's law is not an exception. We looked at for ideal gas, when you have real gases and you have very high pressure or very low temperature, the laws of ideal gas will not be obeyed. But for Henry's law, when you are dealing with very concentrated solutions, or solutions with very extreme pressure, Henry's law will not be obeyed. So Henry's law is ideal for dilute solutions. Henry's law is ideal for dilute solutions. So Raoult's law. So this leads me to Raoult's law. Raoult's law helps to solve some limitations of Henry's law. Raoult's law helps us to solve some limitations of Henry's law. And Raoult's law is ideal when we are dealing with mixtures of liquids. Raoult's law is ideal when we are dealing with mixtures of liquids. So an ideal mixture is one that obeys Raoult's law. Only dilute solutions most likely are the ones that really obey Henry's law. Very concentrated solutions will begin to deviate from Henry's law. Whereas ideal mixtures, okay. So what is an ideal mixture? What are examples of ideal mixtures? So we say dilute solutions obey Henry's law. Ideal mixtures obey Raoult's law. What are the examples of ideal mixture? Well, really in life, we don't have anything that is ideal. But some liquid mixtures get close to being ideal. And when two liquids are very similar and they mix together without necessarily reacting, we say we have ideal mixture. When we have two substances mixing together that are similar, they mix together without necessarily reacting, we say we have ideal mixture. Some examples of ideal mixture is hexane and heptane. They are both non-polar substances. They can be separated by distillation, which is a physical process. So they can mix and become homogeneous. So they have similar electronegativity, similar everything. So this is an example of ideal mixture. So Raoult's law is ideal mixtures obey Raoult's law 100%. Look at benzene and methyl benzene. Their polarities, their everything is close to each other, and yet they will mix together and they can be separated using, especially fractional distillation. You can separate them using fractional distillation. But yet, look at their both benzene, methyl. So their properties are very similar. We have propan 1-one and propan 2-one. You see that they are similar. So when substances that are similar in many respects mix together, they mix very well. We say we have an ideal mixture. In this kind of case, in fact, Henry's law will never have been obeyed because there's no gas here. There's no gas here. Although these two substances are a bit volatile. Hexane and heptane are a bit volatile. So if not that they are ideal substances, Henry's law might have been obeyed. But because they are ideal mixtures, Henry's law will no longer be obeyed. So Raoult's law comes into play. In pure liquids, so let's look at this. In pure liquids, some of the energetic molecules have enough energy to overcome the force on top, and so they escape to the surface. They escape to the surfaces. And so you have some vapor, even though it's a liquid. So even if you have only water, you still have in a container on top of the, and it's not filled to the brim, on top of it, you still have some water vapor on top of it. Because some water molecule have enough energy to escape and stay gaseous on top of it. Now, if the intermolecular forces are weak, you have more escaping and staying on the surface. But if the intermolecular forces are high, fewer molecules will stay on top of the surface. Now, if you have a second liquid on its own, so you have liquid A and liquid B, the same thing will happen. The same thing will happen. You always have some vapor on top because some molecules are very energetic, would escape and stay on top at almost any particular temperature and pressure. So at almost any temperature and pressure, there's always, just that at certain conditions, there might be more. Because they are liquid, maybe if you increase the temperature, there'll be more of such vapor on top. If you reduce the temperature, there'll be less of such vapor on top. If the intermolecular forces are stronger, there'll be less of such vapor on top. If the intermolecular forces are weaker, there'll be more such forces on top. Now, you can imagine these two liquids that each have their own vapor on top. These two liquids have their own individual intermolecular forces on their surface area, on the surface of the liquid. Now you mix them together as seen here. On top of that liquid, let's imagine it's in a bottle. The vapor on top of it will be a mixture of vapors from the two liquids. That's what we're trying to say here. So on top of it, you have, if let's imagine you put 50 mils of liquid A, 50 mils of liquid A, and their properties are similar, like it's an ideal mixture where they are very similar in many respects, then you expect that the vapor would be made up of 50% A, 50% B. And since we said 50-50 mil, the volume of liquid too will be in the same ratio, mixed together. The mixture will be like 1:1. So the forces, the pressure, the vapor pressure they exert too will be equal because they have similar properties. If you follow the logic through, intermolecular attraction between the two red molecules and two blue molecules will be exactly the same if it's an ideal mixture. That is why hexane and heptane get close to ideal behavior because their sizes are similar, molecules interact the same way, the van der Waals force of attraction between them will be the same, and so we get close to being ideal. That brings me to the end of today's lecture. So we have what we call ideal solutions. Ideal solutions happens when the individual components are similar in many respects, are similar substances, they are similar in many respects. And it's only when you deal with such that that Raoult's law is obeyed. Raoult's law came into play to help us overcome the limitation of Henry's law. When you start calculation, you see that they are close to each other but different in some respects. But Raoult's law tried to overcome the limitation of Henry's law. Henry's law tries to tell us the relationship between solubility and pressure. We said certain factors affect the solubility of substances. They are solute-solvent interaction. We have solute-solvent interaction, pressure effect, and temperature effect. Under solute-solvent interaction, we have polarity and molecular weight. We have what we call saturated, unsaturated, and supersaturated solutions. In unsaturated solution, the molecules of the solids are far apart, so they are mixing, moving apart, moving. But as you get to saturation point, the molecules are close enough, but the solvent is still able to dissolve the molecules of the solute and carry it. But the molecules are close to each other. Now, once you reach the saturated point, the next one single grain that you add leads to crystallization. Then you know you've reached the supersaturated condition. And in supersaturated state, the molecules are close to each other such that they clump to each other and are able to be deposited in the container. And then what again did we talk about? We talked about heterogeneous, we talked about mixtures. When you put two things together and they come together, they combine in a way that their interactions are only physical. When they are physical, no interaction, we say we have a mixture. We have heterogeneous and homogeneous mixtures. Homogeneous mixtures, still there's no chemical, but they blend so that you can still separate them by physical methods, but they blend well. So we said example of homogeneous mixtures are tea, and we gave several examples. Air, the homogeneous mixture. So it's a solution. This is a summary of the lecture. That brings me to the end of my part of the lecture. We are still on physical chemistry 2. And from Friday, Dr. Alani will continue from where I stopped. After Dr. Alani, Dr. Duke Eze will be continuing from Dr. Alani. And that after Dr. Duke Eze, you know that you finish physical chemistry 2. Another group of lecturers will now be interacting with you after that. So today is my last day with you. Do you have any questions? You people did not come to see me for slides. So whenever you call, whenever your class rep finds me, I will give you material. But my classes have been explanatory. You might not even need my material. Any question? Any question? Any question? I did not talk about ideal gas. I talked about ideal solution. Ideal solution is when you have two substances that are similar in many respects, and I give you an example, hexane and heptane. They are very similar. They are very similar. They are very similar. So when they mix, they will mix together, especially if you mix them in the same portion, maybe 50 mils and 50 mils, then you have an ideal solution because the contribution of A and contribution of B is exactly the same. So Raoult's law is the one that applies to ideal solution. Raoult's law, you obey Raoult's law totally when you deal with ideal solution. Yes, Henry's law is totally obeyed when you are dealing with dilute solution, where the pressure is not so high. So in dilute solution, the partial pressure of the solute is not very significant. So Henry's law is totally obeyed in dilute solutions. But the deviations from Henry's law occur when you are dealing with very concentrated solutions, when you are dealing with extremely high pressures, you are deviating from Henry's law. So somebody asks, is there material you can use? Yes, any A-level chemistry textbook is just fine for this our course, this CHM 121. Any A-level chemistry. I remember I did chemistry in year 1, and so I went to Yaba, I went to look for A-level chemistry textbook. So look at, you have your handbook, for the faculty. Look at the contents and go to Yaba and look for any A-level chemistry textbook. You would see lots of resources that will explain all the parts that any lecturer will be teaching you in this course. And so I remember as an undergraduate, when they teach me to get practice questions, I'll go to those textbooks, read. Some of you might not, but the books are not so expensive. You see 2,000, you see 3,000. You can get ebooks, but I prefer hard books because I'll be able to underline, I'll be able to, rule. But you can also get ebooks. But any A-level chemistry textbook, just look for the topics and then you see. So you see the topics, and it's like what you did in secondary school, but you notice that we are taking you away. We're adding a little more than what you did in secondary school. So Ababio will not suffice for this course. A-level, we are taking you higher gradually from what you know. We're starting from what you know and taking you higher. So A-level chemistry textbook is ideal. 2,000, 3,000, 4,000, you will get a good, maybe at most 5,000. You get a good chemistry test. We can go to our bookshop or Yaba. You get any good A-level chemistry textbook. You will be good for this course. Then you read it. So when you read what we've taught you, you read our material, read your notes, and then read around the topic in the textbook. You'll be very fine. So I call it a day. Thank you very much, everyone.